Hello everyone. Today we will be going through the steps in order to solve for a specific problem that we were given. The problem we were given is, imagine that you have a chamber in which a chemical reaction is taking place. The chamber is surrounded by 1,000 milliliters. 1 milliliter of water has a mass of 1 gram of liquid water at room temperature, which is 21 degrees Celsius. If approximately 250 moles of a product is produced in the reaction, what change will be experienced by the water surrounding the reaction chamber? Assume that energy absorbed or released by the reaction is either absorbed from the surrounding water or released to the water. The specific chemical reaction that we will be using for this problem is CO2 plus H2O reacts to yield C5H12 plus O2. The elements that are in this equation are carbon, hydrogen, and oxygen. In order to get a better understanding of the elements, I have created a list with the information as shown on the screen. One of the pieces of information is the electron configuration. In order to create the electron configuration for carbon, first we have to look at the diagram on the left where it tells us the order we need to go in. We will be going through the order in a diagonal direction as well. First, we need to know that carbon has an atomic number of 6, which means it has 6 electrons in a neutral atom. Then we must start with 1s. Since s can only hold 2 electrons and we have more than 2 electrons in the element, we write 1s to the second power. Next, we'll look at the diagram again and we see that 2s is next. We already know that s can only hold 2 electrons, so we will write 2 as the exponent. Now we have a total of 4 electrons and we need 2 more in order to reach 6, which is the atomic number of carbon. After 2s comes 2p. When we look back at the chart, we see that p can only hold a maximum of 4. Since we only need 2 more, we only need to write it with an exponent of 2. Next, we will balance the equation. First, we have the equation CO2 plus H2O reacts to yield C5H12 plus O2. When we write out the elements, there is 1 molecule of carbon, 2 molecules of hydrogen, and 3 molecules of oxygen. On the right side, we have 5 molecules of carbon, 12 molecules of hydrogen, and 2 molecules of oxygen. Since the left side doesn't have the same amount of molecules as the right side, we need to balance the equation. In order to do so, we must add a coefficient of 5 in front of CO2. This will then change the amount of carbon molecules to 5 and the amount of oxygen molecules to 11, since there is another oxygen molecule after the plus sign. Next, we must add a coefficient of 6 in front of H2O. The amount of hydrogen molecules becomes 12 and the amount of oxygen molecules becomes 16. Finally, we will add a coefficient of 8 in front of the oxygen on the product side. Now, the left side has the same amount of molecules as the right side, and the equation is now balanced. Now that the equation is balanced, we can use it to find the enthalpy of reaction. In order to do so, we must know the enthalpies of the reactants and products. For the reactants, the enthalpy of carbon dioxide is negative 393.509 kilojoules per mole, and the enthalpy for water is negative 285.8 kilojoules per mole. As for the products, the enthalpy for C5H12 or pentane is negative 35.1, and the enthalpy for oxygen is 0 because it has a standard enthalpy of formation of 0 and it has no change in its formation. Next, we must multiply each enthalpy by the coefficient that is in front of it in the balanced equation. First, we will multiply the enthalpy of carbon dioxide, which is negative 393.509, by 5 and get negative 1967.545 kilojoules per mole. Then we look at the enthalpy of water and multiply it by 6 and get negative 1714.8 kilojoules per mole. For pentane, we multiply negative 35.1 times 1 and get negative 35.1 again because there is no coefficient, which means there is an invisible 1 in front of it. Finally, since oxygen has an enthalpy of 0, when multiplied by 8, it equals 0. Now that we have done all of the multiplication, we can use the formula of delta H equals H products minus H reactants. Before we plug in the numbers, we must add the reactants and products. For the reactants, we add negative 1967.545 kilojoules per mole plus negative 1714.8 kilojoules per mole, and we get a total of negative 3682.345 kilojoules per mole. Then for the products, we add negative 35.1 kilojoules per mole by 0 kilojoules per mole, and we get a total of negative 35.1 kilojoules per mole. Finally, we can plug the numbers into the equation. So we would subtract negative 35.1 kilojoules per mole by negative 3682.345 kilojoules per mole. Or we can also add negative 35.1 kilojoules per mole by positive 3682.35 kilojoules per mole, because when there is a minus sign followed by a negative number, those signs both turn into an addition sign and a positive number. Once we add the numbers, we get 3647.245 kilojoules per mole as our enthalpy of reaction. Since the number is positive, it means that the chamber is absorbing energy from the water and the temperature of the water is decreasing. Thus, it is an example of an endothermic reaction. Also, it is an endothermic reaction because the enthalpy of the products is higher than the enthalpy of the reactants of the system. Now, we can begin to solve for the original question involving the chamber. However, in order to solve for the problem, we must first calculate how much energy is absorbed when 250 moles of product is produced. We can simply do this by multiplying our enthalpy of reaction, which is 3647.245 kilojoules per mole, by 250 moles, and we get a total of 911,811.25 kilojoules. Now that we know how much heat is released, we can use it to solve for the problem as shown on the screen. Now that we know how much heat is absorbed, we can use it to solve for the problem. So in order to find out the temperature change of the water that surrounds the chamber, we must follow the formula Q equals M times C times delta T. In this case, we are solving for the change in temperature, so we must fill in the rest of the missing information. We must substitute Q with the amount of energy absorbed, which is 911,811.25 kilojoules. However, we must make the number a negative because we are focusing on the temperature change of the water. If the reaction is absorbing energy from the water, then the temperature of the water is decreasing. Thus, we must add a negative sign in front of the number in order to show that the temperature of the water is decreasing. Then, we know that the mass of the water, which is 1,000 grams, replaces M. Then, since we are dealing with water in the liquid state, the C, or also known as specific heat capacity, is replaced with 4.18 joules over grams degrees Celsius. Since we are dealing with kilojoules, we must convert the specific heat capacity to kilojoules. To do that, we must multiply 4.18 by 0.001 because 1 joule is equivalent to 0.001 kilojoules. Once we multiply the two, we end up with 0.00418 kilojoules. Once we know this, we can now multiply it by 1,000 grams and get 4.18 kilojoules. Since we are trying to solve for the change in temperature, we must isolate delta T by dividing both sides by 4.18 kilojoules in order to get delta T by itself. We end up with negative 911,811.25 kilojoules divided by 4.18 kilojoules, and we get negative 218,136.66 as our change in temperature. After calculating the change in temperature, I believe the water would go through the phase change of freezing because it started off as a liquid and ended up as a solid. We know this because the temperature of a liquid is 0 to 100 degrees Celsius, and we started with 21 degrees Celsius, which is between the two numbers. Then the final number was less than 0 degrees Celsius, which means that it transformed into a solid. Thus, the phase change that has occurred is freezing. That concludes the video. Thank you for watching.